When we talk about each of the pathways, we're also going to talk about how we control those pathways, and we talk about regulation. All right. There are two major types of ideas about regulatory control that are usually classified, and then one other way things are controlled. But the two things that we think about in terms of control, we think there is at least one enzyme within whatever pathway we're looking in that we can directly manipulate, and we can turn it faster or slower. A lot of times people talk about turning on and off. Really, we very rarely ever turn an enzyme completely on or completely off. We just make it run a little bit faster or run a little bit slower. There's always even in the stopped state or the unactivated state, there's usually what's called a basal activity, some little tiny bit of activity that the enzyme will actually perform. And sometimes we have enzymes that run all the time, things that keep homeostasis going, and so we really don't ever shut them down, but we can get them to run very, very fast at certain times. And so when we talk about regulatory control, we are increasing its rate or decreasing its rate. We can force it to go to 0 in a test tube in the laboratory, but very rarely does it ever go absolutely to 0 in the body. Okay? Two ways that we talk about this when we get to a slide in terms of an enzyme. One is associated with a hormone. Okay? So hormonal control usually will have a hormone released into the bloodstream. It will bind to receptors on the outside of the cell, and it will cause a cellular event through signal transduction. And have you heard that term before, signal transduction? Where it's kind of like a domino effect, where one thing activates another, which activates another, which activates another. And usually the outcome is this: the enzyme is covalently modified. Okay, covalently modified. What does that mean? Almost always, but not always, but I mean a whole lot of times, you do this. You either add a phosphate onto the enzyme, and you control its activity either up or down, or you take a phosphate off. Okay? That phosphate that is placed on that enzyme causes a little bit of change in the three-dimensional structure. We call that a conformational change. And it's a powerful regulator. All right? The next type that we talk about is something called an allosteric regulator. Okay? And allosteric effectors can be either stimulatory or inhibitory. And so sometimes we make them go faster, sometimes we make them go slower. Now, remember, an enzyme is a protein, and it has a pocket where the substrates bind. Okay? And where the substrates bind is where the active site and the reaction actually happens. The allosteric effectors do not bind at the active site, it binds somewhere else on the protein. And it will either make the shape more optimal to make the reaction go, or less optimal. And again, it's a little change in the structure. And so most enzymes have both a covalent modification and or a interaction with some sort of molecule that will turn them on and off. So those are the things that we look at. Hexokinase was just a little bit different. There was one more element in which it was controlled, and that was by its ability to bind the substrate, or its affinity. And we measured that by looking at the measure of Km, the concentration at which it made half the activity. And if you have a very low number in terms of Km, that means the enzyme has high affinity, and it will go fast when there's lots of things around. Or if the Km is high, it has lower affinity because it doesn't bind as well. Okay, and so we manipulate enzymes with those particular types of forces. And so the next enzyme in glycolysis that we are looking at, and probably the most powerful regulator, is the enzyme phosphofructokinase 1. Remember, it takes fructose 6-phosphate, and it creates fructose 1,6 bisphosphate. the has ADP is a product, ATP is a reactant, and remember, this class of enzyme is called a kinase. Kinases tend, or the classification of kinase is to add a phosphate to the substrate, whatever that is. All right, so there are some control points in this particular enzyme, and the control points will be allosteric effectors mainly. And so we have things that will speed it up, and we'll have things that will slow it down. Speeding it up, okay? Some things can be very logical. I think you might be able to understand why this concentration and that concentration, if those go up in the cell or high in the cell, glycolysis is actually breaking things down, and we're going to make ATP. And so if we don't have a lot of energy, we're going to take all our sugar and break it down until we make ATP. On the other hand, ATP, if we have lots and lots of ATP, we may not need to use our sugar to make ATP. At that point in time, we may need our sugar and store it. And so for later use, because right now we're flush with ATP, so we are not going to continue to break it down. These two, though, are ones you might not recognize or have any reference to. The citrate, I'll give you a preview. Everything that ends up in pyruvate will, in a very short period of time, become citrate. Okay, so we're going to feed pyruvate into citrate. That's the next cycle. If citrate starts to build up in concentration inside the cell, what that means is the next phase of the process is not going real well. Okay, I'm overwhelming that next phase. So if I'm overwhelming the next phase, I don't continue to feed it because I'm already behind. And so it's feedback to say, hey, slow down, I can't keep up with all the material coming at me. The fructose 2,6-bisphosphate was a surprise to everybody when they actually found that, and we'll look at that in just a moment. All right, if I look at the activity of the enzyme based upon the concentration of the substrate or the reactant, as I increase the reactant, the velocity of the reaction goes faster. All right. If by chance I have low concentrations of ATP, I go faster, making more of glucose break down through glycolysis. If I have high ATP, it tends to slow the reaction down. All right, now how is that particular process actually working? You can see if there's lots of ATP, it binds at other sites and it excludes the fructose 6-phosphate. It actually changes the shape of the active site so that it doesn't fit fructose 6-phosphate very well. And if fructose 6-phosphate doesn't bind, it won't be phosphorylated. Okay? On the other hand, ADP, when it binds, all right, in the regulatory places, and here's the regulatory, it will make the fructose 6-phosphate binding much better, meaning the shape of the pocket now wants to bind fructose 6-phosphate, and then I will phosphorylate that to produce the product. Okay? Now, there is another term on this slide, R state, T state. The R state is referencing back to relaxed state. The T state is referencing back to the tensed state. This was all reference to hemoglobin. Hemoglobin in the tense state, how does it interact with oxygen from what you learned in your previous class? In the tense state, does hemoglobin want to bind oxygen or not want to bind oxygen? It doesn't want to bind oxygen. In the tense state, hemoglobin actually makes lots of salt bridges to make the physical protein rigid or tense. In the relaxed state, it tends to bind to oxygen, and what actually happens is, in the relaxed state, the shape of hemoglobin moves and is actually loose and actually binds to oxygen better. So the relaxed and tense state refers back to hemoglobin's structure. From this point on, we can describe an enzyme as relaxed, bind substrate faster, meaning it will work faster, or tense state, bind substrate less likely, and it will be less active. And so T and R has nothing to do with the enzyme structure. It has everything to do with, does it work fast or does it work slow? Okay. There's also one other inhibitor that wasn't on the slide, but it's on this one. Protons. Okay. One thing that inhibits glycolysis is protons. All right. Where glycolysis occurs quite often is in muscle. Okay. In the muscle, you break down and use ATP, all right, and you break down sugar, the glucose, to get ATP. But if you work intensively hard and ultimately you have to react things with oxygen, if you work out really, really hard and really, really intense, you go from an aerobic kind of workout, one that has oxygen, to an anaerobic workout. In an anaerobic workout, you make an acid. Do you know what acid you make? Lactic acid. And you're working out hard and you feel the burn, okay? It's that acid that is indicating, hey, you are not using all of the energy of glucose efficiently, okay, because you don't have oxygen. You're working too fast for oxygen to be replenished. You make lactic acid, the pH becomes more acidic. That slows down glycolysis, okay? And so that's another regulator of glycolysis. Here, citrate is the molecule in the next cycle. If I'm feeding that next cycle and it starts to build up, it tells this cycle to slow down. It tells glycolysis to slow down. All right, when we actually purified phosphofructokinase and studied it in the test tube, okay, it really had a much different reaction to glucose. It went, actually went a whole lot faster or a whole lot slower in terms of some of the regulatory things that we thought. What we didn't know and only discovered in 1980, which is not too long ago, especially since most of the things that we learn about are found in the 30s and 40s. This particular molecule, something called fructose 2,6-bisphosphate, is an activator. And it is the most powerful activator of all of the regulatory molecules, even more than the presence or absence of ATP. Fructose 2,6-bisphosphate kind of sounds just like a glycotic intermediate, but it isn't. It is only a regulator, okay? Because the enzyme that we're controlling right now is fructose 6-phosphate to fructose 1,6-bisphosphate. That's the enzyme that we are regulating. To make this molecule right here, we're going to take fructose 6-phosphate and make fructose 2,6-bisphosphate. Those reactions look really similar, don't they? Right? We add a phosphate to it. What enzyme adds a phosphate? A kinase. What is the substrate? A fructose that has a phosphate on it. And so the enzyme that's going to work on this is phosphofructokinase. Wait, we just said we're controlling phosphofructokinase. We're going to actually talk about phosphofructokinase version 2 is what's going to control all of this. All right. This particular molecule, this small regulatory molecule, does two things. It makes the phosphofructokinase go fast. That means it makes glycolysis, breakdown of glucose, go fast. at the same time. We aren't going to learn this pathway, but in opposite, this same regulator at the same time will stop the process of making sugar, gluconeogenesis, the exact opposite. This is wonderful. In metabolism, we never ever want to have both the breakdown and the synthesis of one molecule going at one time. Why wouldn't we want to do that? Why wouldn't we want to have the breakdown and the synthesis pathway going at one time?
Because if you're making it, then destroy it.
You make it and you destroy it. You make it and you destroy it. And do you know what you use? Energy. It is an energetically unprofitable thing. So having one molecule signal both start this one and stop its reverse is wonderfully efficient. Okay, it's called reciprocal regulation. Okay, and so this small molecule is really important. The formation of that molecule happens with an enzyme called phosphofructokinase version 2, or FPK2. Okay, so the kinase puts it on. And to break that down, you need an enzyme called fructose bisphosphatase version 2. And a phosphatase class is an enzyme that takes off a phosphate. All right. Now, most of the time we told you an enzyme is very specific, has one function, and that's how we learned each enzyme. They're very specific and they do one reaction. This particular set, the kinase and the phosphatase enzyme, we discovered was in one protein. It's a protein that has two domains or two pieces to it. One piece is the kinase that makes the 2,6, and one is the phosphatase that breaks down the 2,6. So I have two active domains, a kinase domain and a phosphatase domain, and I have one regulatory domain. This is the important piece right here, between 1 and 32 amino acids. Okay? One regulatory site and one catalytic site. Never is the kinase and the phosphatase active at the same time. Okay? It is controlled by the regulatory site. The regulatory site has a serine, represented by that hydroxide. The serine can be in the hydroxide state, or it can be in the phosphorylated state. So this particular set of two enzymes in one protein are controlled by a phosphorylation or a covalent modification. Remember what causes covalent modifications? What causes the covalent modifications? I've been so effective already in this lecture. Hormonal control. So these are the hormones: glucagon and insulin. Okay? Insulin, well-fed state. Okay? If I am well-fed, all right, then I want to break down lots of these molecules to make lots of ATP so I can do synthesis. Okay? How do I do that? The insulin will use a phosphatase and make it the unphosphorylated version. The unphosphorylated version creates the 2,6, which makes glycolysis go. Okay? Insulin will affect both liver and muscle. We have receptors for insulin in liver and muscle. All right? In liver alone, because muscle doesn't have a receptor for glucagon, in a starvation state or you're really, really hungry, glucagon is given out. You have low blood glucose. This causes a kinase to work on the enzyme to put a phosphate on this enzyme. I have the phosphatase there, and it breaks down 2,6. If I have no sugar in my system, I don't have a lot of energy, okay, in our system to break down, I will phosphorylate this particular protein, make it work as the phosphatase, make the 2,6 go down in concentration. I stop glycolysis in the liver, and I stimulate gluconeogenesis in the liver so that I can feed it to the bloodstream and make sure my brain keeps working, because brain uses glucose exclusively. And so in starvation states, I force the liver to make sugar so it can go to the brain. All right? So ultimately, the 2,6-bisphosphate is controlled by the signal of hormones. Do I have lots of sugar? Send out insulin. Make 2,6, make glycolysis go. Or I'm in a starvation state. Break down the 2,6 and make sure glycolysis stops. Glucogenesis, the reverse, start. The last enzyme that actually has some power in controlling the whole process is pyruvate kinase. Okay? In that, the pyruvate kinase takes, here's where biochemistry really gets bad. What is PEP? It's something that totally made up, right? We have rallies of them. Yeah, it's not about football. What's PEP? We've got all these acronyms. Phospho, enol pyruvate. Okay? And that phosphoenol pyruvate will react with what? To make pyruvate. ADP to make ATP. Whenever you make or break ATP, it's a very energetic process. Okay? So once you go down that road, you just can't go back. And so this one needs to be controlled. Okay? What controls it? Well, there are some things that make it go and things that make it stop. Okay? Why does fructose 1,6-bisphosphate make it go? What is it? Well, if you've got lots of starting material, it tends to make the whole process go. And so this one's a feed-forward regulator. I have lots of starting material. Let's break it down. Okay. Why would ATP slow this down? Because ATP is part of this slowdown product. What's the purpose of glycolysis? To make ATP. If I have lots of ATP, don't make it. Okay? Now these are a little bit more challenging because you may or may not know how metabolism works. All right? We're talking about mainly this is the muscle. The first line of energy in the muscle is glucose. It's very fast to be accessed. Okay? Over time, your body tends to do this. When you start running, you can use glucose, you can go really, really fast, but you can't maintain that speed because what you do is you shift to your other two energy sources. What are your other two energy sources other than carbohydrates? Fat and what are the things you eat? Protein. Okay. Now, we can extract lots of energy from carbohydrates really, really quickly. But when you shift over to using fat and protein, okay, it actually is a slower process. Okay? If the doctor tells you to exercise to lose weight, how long do they tell you to exercise?
30 minutes a day, right?
At least 30 minutes a day. Why in the world do they tell you to work out at least 30 minutes a day? Well, in very short workouts, okay, 10, 15 minutes, you use lots and lots of carbohydrates, okay? What do you not use at all? Fat. Okay, now, what would that workout do for you? Okay, it could tone you, and it could prevent you from making any more fat for excess glucose that you have in your system, okay? So you probably won't gain weight other than if you gain some muscle weight, okay? But you don't get to the point of actually breaking down fat, which is really what the doctor wanted you to do. Over a period of time, your metabolism starts shifting from using the sugar to start using the fat and protein sources, okay, in the muscle. But that means you have to send a hormone to the fat, have to break down the fat molecules, have to carry them in a protein, have to deliver them to the muscle, and it has to get inside the muscle. Same things with amino acids. If by chance you see fats being transported to the muscle, what does it do to glycolysis? It slows it down. Because this is an indication that you've gone long enough to actually start utilizing the fat rather than the carbohydrates. All right? Acetyl-CoA is also a breakdown product of fats, and so that's an indicator that fats are being used, and that slows it down. And then ultimately, alanine is one of the 20 amino acids. They could have chosen any one of them, but if alanine is there, it binds to this enzyme, meaning that mobilized amino acids are there to be broken down, and so it slows it down. So when I start getting protein and fats in the muscle, I start to conserve my glucose. Okay? There is one other regulatory event that can occur only in liver because glucagon has receptors in liver, and I can covalently modify, and do you see a hormone takes it from a dephosphorylated state to a phosphorylated state, and so I turn it off there. That won't affect muscle. Okay? And so those are the three key. The most powerful regulator of this process is the phosphofructokinase 1. All right. As we look at the reactions of glucose through glycolysis, okay, glucose to glycolysis, through glycolysis to pyruvate. I make a little bit of ATP. That's wonderful, okay. But for this reaction to happen, you have to have one more reactant, and that's NAD+. Okay. This is a limiting factor in your metabolism in the muscle. Usually, you have a ton of glucose in terms of how many glucoses are there. This right here becomes the one that runs out first. In a reaction, what do we call that in general chemistry? The limiting reagent. Okay. Ooh, this all does connect at some point in time. Okay. Now, for this to be regenerated, okay, the best thing to do is to take the electrons and go through the electron transport chain and make them end up into oxygen. That's the best way for this NAD+ to be regenerated to come back and do the reaction. Okay? But you can overwhelm the system and have lots of NADH produced. The NADH comes down here, and if there's no oxygen, I can't do this reaction here because I have no NAD+. This is where the body starts doing something weird. It has the ability to react the NADH that has the hydrogen with some of the pyruvate to make NAD+ to break down more, but the product here in the body is lactate. Lactate is a dead-end product in the muscle. It cannot be processed in the muscle anymore. It actually builds up in concentration and actually can cause contractions that don't release, cramping, right? And it would have to be diffused out of the muscle, go through the blood system back to the liver, and be reconverted into something that we can use. It's a long-term process. Okay? And so lactate is one of those toxins in your system. If you've ever had a massage, okay, after the massage therapist gives you something and tells you to do something. Does anybody know? Drink lots and lots of water. The reason is, one of the things that they do in the massage is what you're trying to do is invigorate more blood into the muscles to work out those knots. Those knots have this lactic acid in it and other things. And so as you manipulate the muscle, you get that blood flow, you extract all of those molecules into the bloodstream. And if you've had a good massage, there's a lot of that material in your bloodstream. And so you drink lots of water to dilute it and to get it out. Okay? And so that's how we can regenerate some NAD plus and make some energy, but we only make 85 kilojoules out of the 2,840 kilojoules available. Anaerobic workout is not very efficient. Okay? And so I would rather have aerobic workout. Now, other things, this process right here is called fermentation in our bodies. All right? There are other entities like bacteria that will do fermentation differently. Glucose goes to pyruvate. Pyruvate will react. CO2 will be lost. And I will take the NAD and convert it to NAD plus so I can continue the cycle. And look at what it makes. Okay? Totally different. Now, just think about this. What if we had the enzyme here? Do you think more people might work out? Think about that. If we actually have this enzyme here, and you work out really, really hard, you make this in your system. That would make it, one, funny, and two, dangerous in the gym. Okay? And so, the actual production of ethanol using bacteria and the enzyme there is one of the first biologically commercialized process. And the enzyme actually has a zinc cofactor. Okay? Remember, an enzyme wants to make the transition state more stable. And so what happens is the zinc will coordinate to the electrons on the oxygen, because metal centers love electrons. That allows this electrons to be pulled by zinc, which actually pulls all the electrons, which makes the carbon more partially positive. This hydride that will attack, which is a nucleophile, wants to attack something that's more positive, and even when the electrons come up, it's not a full negative charge because they're really being coordinated to the zinc. And so that transition state is stabilized. And when the transition state is stabilized, the electrons can pick up a proton and we can create the ethanol. All right? And so that's how yeasts regenerate the NAD plus to break down the glucose. Actually, when my dad was stationed in Puerto Rico, we went to San Juan and took a tour at the Bacardi plant factory. It was actually kind of really neat. And we walked up, and they walked you up there. I don't know if they do this anymore, but there was a 3-story vat that was about almost the diameter of this room. And you got on top of that, and you saw the liquid with the mash in there and the yeast, and it looked like it was boiling. Okay? It wasn't heated at all. The boiling was the CO2 coming off, and in the process. Now, you walked by that big old vat that was opened, and just by smelling it, you could probably not drive after that. But it was kind of a neat process to see that. All right. We can't do that for good or ill, so we allow the hydride to react with the pyruvate to make the lactic acid. Okay. And so we only extract a small amount of the energy doing that. But this allows us to do this. If by chance we're walking in the jungle and the lion comes at us, we run really fast and we run even past our capacity to breathe, and it allows us to extract a little bit of energy so that we can keep running. Inefficient, and that burn is the balance to tell you to stop because you're not doing it as efficiently, but sometimes you run through the burn, especially if something is chasing you, right? And so we can get some other sugars entered into the mix. And again, most of the time we don't actually eat glucose directly. The two most often eaten ones are, we talk about lactose from milk and sucrose, our table sugar. Wherever the sugars are coming from, especially in the disaccharides, what we are eventually going to do is convert them into one of the structures within glycolysis. And so if by chance you produce glucose by breaking them down, and so tetralose would be broken down by tetralase, sucrose by sucrase, lactose by lactase, one of those sugars on every one of them at least is glucose itself, and it's phosphorylated by hexokinase, and it's in the glycolysis. The other sugar, depending upon where it is and what it is, tetralose are both glucoses. The sucrose puts out fructose, okay? Fructose is almost a glycotic intermediate, right? But it isn't, and so it has to be processed. And there's two pathways to do that. One, it can be phosphorylated to the fructose 1-phosphate using fructokinase, okay? And then that can be broken down by a fructo-1-phosphate aldolase. Remember, and we had an aldolase that was right here, and it made dihydroxyacetone phosphate is one that we knew about, and then glyceraldehyde, but we made glyceraldehyde 3-phosphate. So this glyceride has to be phosphorylated, and we're now in glycolysis. There's also one special tissue that allows fructose to be worked on by hexokinase to go directly in. Almost all tissues do this one. One special tissue allows that pathway to work. And then galactose, on the other hand, I've got to show you, and I've got a slide for that. It's kind of weird how it processes in, but it will become glucose 1-phosphate, become glucose 6-phosphate, and enter in glycolysis there. The two pathways for fructose, okay, the hexokinase, the not very often used pathway, only happens in adipose tissue, okay? If by chance fructose can get into adipose tissue, fructose will bind inside hexokinase. Well, I told you hexokinase wants to bind glucose, right? And actually it has 20 times more affinity for glucose, so if glucose is ever around, it will never bind fructose. Only in the fat cell, in the adipose tissue, will fructose ever become high enough in concentration with absolutely no glucose, and it gets worked on right here. Okay? Glucose is only transported in times where you're making fats, and you break them down to make the glycerol to make the alcohol to put the 3 fats on it. So most of the time, adipose tissue has no glucose. The majority of the time, fructose goes through this particular pathway. Galactose is kind of weird, okay? What in the world is the difference between galactose and glucose? Okay, take a look. Here's galactose, there's glucose. This one has a phosphate on the 6th position. So if there was a phosphate there, it would be the same. So hydroxide up, hydroxide up. Hydroxide down, hydroxide down. Hydroxide up, hydroxide up. Hydroxide down, hydroxide up. It is only different in one hydroxide, whether it is up or down. Okay? Those two sugars are related, and they are called epimers. You remember that term? It's one of those stereochemical terms. It only applies to sugars. So all I have to do is flip one. Well, there's an enzyme that changes epimers. It's called a epimerase. Okay? And so we're just going to do a epimerase, but it's not that simple. So here's what happens. Galactose will be converted into galactose 1-phosphate, done by, what is that enzyme, class? Kinase. All right. Well, I put a phosphate in the wrong place, but that's how it has to happen. Then I react it with this, a glucose that has a adenine ribose 1,2-phosphate, diphosphate. Okay, so a glucose on a diphosphate, an adenine or ADP. Oh, sorry, that's not adenine, that's U, not A. It works and has the same kind of energy values. All right. The galactose will react with this substrate, and what will fall off is glucose 1-phosphate. What will be formed is galactose now here on the UDP. All right. If I follow this down, glucose gets converted into glucose 6-phosphate from the 1 version. It's a mutase. We saw a mutase in glycolysis. What was the intermediate for the mutase that went from 2-phosphoglycerate to 3-phosphoglycerate? Do you remember that reaction? It looked like the phosphate from the 2 moved up to the 3, right? But did it? No. There was an intermediate that had double phosphates on it. Same kind of reaction will happen here. All right, we follow this galactose, we put it right here. Okay, we put it on the UDP because the epimerase has to have the UDP in it for it to fit inside the enzyme. Once this fits inside the enzyme, this galactose, that hydroxide gets flipped, and it is now glucose. It's stuck onto this until another galactose comes in, does a reaction, and it's released to come out. So we've got this circle that has to happen for the glucose to finally come off. It's kind of complex to get that done. And it gives rise to a particular disease that we see. Okay, it's a multi-step process. Sometimes we have the absence of the galactose 1-phosphate uridyl transferase. Oh my goodness, what in the world was that? The galactose 1 uridyl transferase. It takes the galactose 1-phosphate and reacts it with this glucose thing to give off glucose. This enzyme stops working. That means none of this happens and none of that happens. That means I can go from here to there, and that is it. Okay? Now, what consequence does that have? Galactose starts building up in concentration. Usually galactose is a real small concentration. If it builds up in concentration, it binds to a whole nother enzyme that it really isn't supposed to bind to. And it gets converted into an alcohol. Okay? Which is a dead-end product. Nothing in the body can break that down. It just doesn't fit into any other enzyme. If this particular molecule starts building up in concentration, you can suffer from enlarged liver, jaundice. It tends to cause mental retardation. And one other thing happens is that that molecule tends to precipitate in the lens of the eye, and it is one mechanism to form a type of cataract. So what in the world would be the treatment to stop galactosemia? Yeah, just not eat it. Okay, so which was the disaccharide that had the galactose? Which one had galactose? Yes. So, no ice cream, no milk, no cheese. Okay? That does not sound like a fun time. But if you're alive and you don't eat that, that's kind of a balance, yeah, you know? I think it's okay. Now, but no, that's good. I'll just have lactose or lactate milk, right? No, why can't you have lactate milk? If you're lactose intolerant, you can have lactate milk. It breaks down into galactose, but galactose is still there. Okay, so you couldn't even have all of those things that would help someone who's lactose intolerant. All right, and so that becomes, you know, I would try to think of a diet that had all of those things absent, and I'm like left with nothing that I would eat. I mean, it would be horrible for me to think about that. All right, one more thing. I have handouts. Ready for your first exam? No. Not yet. Would you cry? Probably. Yeah. All right. So, as I've gone through glycolysis, I've attempted to identify the kinds of classes of enzymes that we have seen. Okay? In biochemistry, they have done this extensively, okay, and placed every enzyme into classes. There are 6 major classes of enzymes, okay? And so let me move to something that is similar to yours, okay? So there are 6 major classes of enzymes. An oxoreductase, meaning that we're going to have reductions. Do you need one more? We're going to have oxidation reduction reactions. All right. In that, electrons move. And we have seen that up to this point in terms of a hydride moving. And so the enzymes that we looked at up to this point in time were the dehydrogenases, in which there is an electron acceptor where a hydride is moved around. Okay, there are transferases, hydrolases, lysases, isomerases, and ligases, all of which do certain things. And so transferases transfer a group from one entity to another. And so an example of transferring a group was a kinase. Okay, a kinase is carried on an ADP, a phosphate is carried on an ADP, and that phosphate is transferred from the ADP to another, usually in this case an enzyme, or a sugar we saw. And so it carried the phosphate. So it's under the big class of transferase, under a specific class of kinase. Hydrolase are ones that add water to something and something falls off, is broken off. We saw a phosphatase is a class of that. There's a phosphate on an entity. To break that phosphate off, I have to add water. Okay? We haven't seen a lyase at this moment in time. It adds or removes elements of water or ammonia or carbon dioxide. We will see some. Oh, sorry, no, we did. We have an aldolase. It actually has aldehydes fall off. We have seen an isomerase. We have not seen at this moment, I don't know if we've seen a ligase at this moment in time. All right? And so there are 6 major classes. Now, the examples under these, all right, I gave you 4 for the oxoreductases. There's not just 4. There's like 22. And each one of those have subclasses under that. And so the oxoreductase is a 1. The main class would be another number, okay? And so you could have an enzyme that is 1 dot, and then the dehydrogenase might be a 2, so the enzyme is a 1, saying it's octoreductase, dot 2, it is a dehydrogenase, dot, and there's 2 more numbers. And every enzyme has a 4-number code to classify what it does, all right? I don't want you to learn every single enzyme and what is classification, but I do want you to be able to identify what that enzyme is and what kind of big classification it was under. And so if we looked at, let's say, hexokinase, the first reaction that is in glycolysis, it would fall under the kinase, okay? And what it would do in terms of its mechanism, how would you describe that mechanism for a kinase? What does it bring in as a reactant for that enzyme? ATP, okay? And then what do you react it with? Okay, so it's the glucose right there, right? Where does it actually react on a glucose? What functional group? A hydroxide, an alcohol. And so it brings in an ATP, it reacts with an alcohol by deprotonating the alcohol and having the alcohol attack at the alpha, beta, or gamma. Gamma to produce ADP. Okay? And so you can describe in general what that reaction does. It takes an alcohol, it takes off the proton, deprotonates it, it brings in an ATP, gets attacked at the gamma phosphate, ADP is a leaving group. Okay? When you look at any kinase from this point on, that's what you're going to see. Doesn't matter what the name in front of it is, that's the generalized reaction that occurs with a kinase. And we are going to see lots of kinases. All right? Isomerases. What did I tell you happened in isomerases in their reactions? What did it do? No, it will, but how does it do it? You do what first? You take a deprotonate, and then you protonate. And sometimes one doesn't get it done, does it? So then you have to deprotonate and protonate, deprotonate and protonate until you get done. Okay? And so in isomerase, the ones that we've seen, you just deprotonate and protonate. All right? And so as we move into different kinds of enzymes, it would be good to kind of get an idea. Okay, if you see this kind of enzyme, what did we see in the reaction? How could we classify what happened? All right? And as you learn that and you see the name of the enzyme, it can give you a clue as to what might be happening inside the reaction that's happening. Now, most of the ones that are on this list are ones that happen quite often. We may find some enzymes that don't have one of the subtypes, but it might be under the bigger class as we go through. But I want you to keep a running tab of, as you see new enzymes, try to find out or try to visualize or describe what's happening. Now, if we look at names of enzymes, okay, most of the time an enzyme has an ACE at the end of it, okay, and it's attached to what the substrate or the reactant is. So urase or sucrase, okay, it takes sucrose and it has ACE to it, so it's an enzyme, and you kind of get an idea of what's happening, okay? And so if you take a look, another example they put on there was lactate dehydrogenase. Okay, lactate is going to be the substrate, and the dehydrogenase is going to move a hydride around. All right? So a lot of times the name tells you kind of where it's going. Although some enzymes have what are common or trivial names, something like trypsin or pepsin, That doesn't tell you anything, but hey, that's what it gets called. Just like we call water, water, not dihydrogen monoxide. Okay? There is a systematic name, which gets really complicated. It names every part of the reactant, every part of the all the substrates, and formally names it. It tells you exactly what's going on, but no one ever uses it because it's too long. And so a lot of times we're back to the common names or the recommended names. And so they can be really, really complex. As you can see, last thing, hexokinase down here, not there, has an enzyme class, the EC 2.7.1.1. That's its official classification, and it has an official name, but we call it hexokinase. All right? And so I just wanted you to know why we see different names in textbooks. Sometimes they use the formal name, sometimes they use the common name, sometimes they use whatever they want to do. And unfortunately, it's that way in the journal articles too. And so sometimes it's hard to find what you're looking for.